Hi dear students. So in the last class we have discussed about the Young's modulus. Now let us see the determination of the Young's modulus of a material of a wire. Already we have done the practical regarding this experiment. So we are going to find out the Young's modulus of a wire. So let us consider the B as the wire, and there will be another wire for the reference. So the elongation happened will be measured with the help of the scale, the vernier scale which is attached with the wires. So here we are suspending the mass on the wire beam. So that will act as the deforming force. And as you are increasing the mass, the wire will get elongated, or the stretching of the wire happen. So the mass into the gravitational acceleration, that is the force acting upon the wire B, that is the tension upon the wire B. So mg is the force over there. And if the radius of cross section, if the radius of the cross section of that wire, if it is r before elongation, that means for the normal wire, if the radius of the cross section, if it is r, then its area of cross section will be pi into r square. Pi into r square will be the area. Then the stress value will be, that is the force divided by the area, force per area, that will be m into g divided by pi r square. The longitudinal strain value will be the change in length, that is here suppose the elongation happened, if it is delta L, that length, then divided by the original length, that is the strain value. Then you know that the modulus value, here the Young's modulus value will be the stress value divided by the strain value. Here the stress value is represented by the letter sigma, and the strain value is represented by epsilon, and the sigma by epsilon, that is the stress by strain, is actually force per area divided by change in length by the original length. So the equation we will obtain as mg by pi r square into L by delta L, that is mg L divided by pi r square delta L. That is the Young's modulus value in the case of a wire. Means practically or experimentally we can find out the Young's modulus of a material of a wire by this method. Okay. Now let us come to the next modulus, that is the shear modulus. Shear modulus, the definition for the shear modulus is given here, that is the ratio of shearing stress to the corresponding shearing strain is called as the shear modulus. And it is represented by the letter G, and the another name for shear modulus is the modulus of rigidity. It is known as the modulus of rigidity. So the shear modulus capital G, it is equal to the shearing stress divided by the shearing strain. Here the shearing stress value, it is force per area, and the shearing strain value we have already seen that is the displacement occurred for the upper layer divided by the length of the particular material, or the height of the particular material. So here you can see that here when the shearing force or shear force, when it is acted upon that particle, there is no change in the position of the lower portion, but the upper portion is get displaced. Then the displacement occurred, it is delta x, that is the displacement occurred from the original position to the current position. The displacement occurred, it is delta x. And the height or the length, it is L. Then the shearing strain value will be delta x divided by the L. Okay. So the shear modulus value will be F by A divided by delta x by L, that is F into L divided by A into delta x. Now when we have discussed the shearing strain, we have seen that the delta x by L is actually the tan theta. Delta x by L is actually the tan theta, where the theta value is approximately, or it is approximately to 0, or it is very less. The theta value is very small. Hence the tan theta value will be equal to theta. We can consider the tan theta as theta. Then G will be is equal to F by A all divided by theta, that is F by A into theta. And then the shearing stress value, that is the F by A value, can be determined as G into theta, where theta is the angle of the displacement. Now the SI unit of shear modulus is Newton meter raised to minus 2, that is, otherwise it is Pascal. And in the case of majority of the material, in the case of the majority of materials, the shear modulus will be lesser than the Young's modulus, and maybe 1 by 3 times of that of the Young's modulus. So these are the major things regarding the shear modulus. Now in the table number 9.2, for various materials, the shear moduli value it is given. Just to go through that one once.